Hello everyone, welcome to our project pitch. My name is Lapitsala Chimpad.
Hi, and my name is Yanticha Pahuwattanakorn.
Today we're excited to introduce you to Pitch Hangman, an interactive game that blends classic gameplay with music learning, all powered by Arduino. Our project explores how we can make learning music more engaging by combining it with the thrill of guessing game. We took inspiration from the classic game Hangman, where each wrong guess brings you closer to losing, and added a music twist. Instead of guessing letters like in regular Hangman, you listen to notes and try to guess them. It's a fun way to get better at recognizing pitch and understanding how frequency works.
Next, the method for starting game will be explained. When the board is powered on or reset, the LED screen first display a welcome message to greet the player. After that, when the player presses the start button, the game begins. A red LED light up, a musical note played through the buzzer, and at the same time, the Hangman game interface appears on the LED screen. The music helps create excitement as the game starts. Next, the player then presses the corresponding note based on what they heard, holding the note button and pressing the mic button once to input the sound. The LED shows the note that was just played, along with the detected frequency in heard. This process is repeated for all notes in the sequence like that. Once done, player can press the check answer button. If the note matched correctly, number sign symbol appear for each correct note, and the score is shown on the 7-segment display. What if the player guesses incorrectly? If the player presses the wrong note, an exclamation mark symbol will appear on the incorrect note during checking, and the 7-segment will count point only for the correct ones.
The purposes of our project are 1. Practice listening skill and pitch recognition of musical note. 2. Learn musical note through a fun and challenging game. 3. Promote the use of microcontroller, especially Arduino, in interactive game development. Here is the equipment. We have a 0.96-inch OLED display, a passive buzzer that can play notes at different frequencies, and a KY037 sound sensor module. We are using two main boards, an Arduino Uno R3 and an Arduino Mega 2560. We also included a potentiometer, push button switches, LEDs, a 7-segment display, some wires, and 330 ohm resistors. We selected note frequencies from C5 to B5, a range that provides both clarity and accuracy for detection. As you can see, each note has a unique frequency. By matching the detected sound to these values, we can figure out which note was played, and that's how we check if the player guessed it correctly. Here's an overview of our circuit and the code structure behind it. This is the physical prototype of Pitch Hangman. As you can see, you might be wondering why I used two Arduinos. At first, we used only one Arduino, but we quickly ran into a memory limitation. We look back at the OLED display, which had resolution of 128 by 64 pixels. After calculation, we found it used up to 1024 bytes of memory. Since the Arduino Uno has only 2 KB of SRAM, the OLED alone consumes about half of it, which is too much for a single component. So we decided to use two Arduino boards and split the workload. Then the question became, how do we get Uno and Mega to talk to each other? Let's show how we made that possible. In our setup, we assign the Arduino Uno as the sender and the Arduino Mega as the receiver. The Uno collects input from the sound sensor and sends the data to the Mega. The Mega takes care of the gameplay, handling output like displaying notes and showing score. These two boards are connected using the TX and RX pins. Specifically, the TX transmit pin on the Uno connects to the RX receive pin on the Mega. If we want two-way communication, we can also connect RX on Uno to TX on Mega. This type of connection is called serial communication. It allows the two Arduinos to exchange data one bit at a time over the TX and RX lines. Before we get into the code, let's clarify the roles. The Arduino Uno acts as a listener. Its main job is to receive input and send data to serial communication to the Mega. The Arduino Mega reads incoming data using its multiple serial ports, serial 01, 02, and 03. Each of these ports can be used to communicate with different devices.
Now, let's take a look at the core of our project, the Hangman game code. We program the game using Arduino, which is based on C++. This is Uno act as the sender. It captures sound via microphone, analyzes frequency using FFT, detect musical note, and send the data to other devices. The code starts by importing the Arduino FFT library to convert sound from the time domain to the frequency domain using FFT. We define two constants. Samples is set to 64, and sampling frequency is 4000 Hz. This is control how we sample and analyze the sound. An FFT object is created, and we set up timing variable like sampling period and microsecond to control sample timing. Sound data is stored in variable, while we IMAX is filled with 0 for FFT use. Detect node hold up to 16 nodes per block, and blocking will keep track of how many have been detected. In the setup function, we start serial communication config your button pin, and calculate the sampling period for consistent data capture. In the loop function, the program checks if the button is pressed. If it is record start, it then collects 64 samples from microphone and store them into variable with IMAX set to 0 for FFT processing. After that, FFT is performed to convert the data into a frequency domain, and the peak frequency is sound using FFT.measure peak. This frequency is then converted into musical note and played on the serial monitor. The note is stored in the detect node array, and recording continues until the button is relayed. Finally, when recording ends, the program finds the most common note detected during that session. Display the summary. Finally, the program displays the most common note detected in the serial monitor in this format: serial.bin summary and serial.bin out in the summary. For example, it would display summary C5, indicating that the most common note detected was C5. Get note frequency. This function maps frequency to musical note based on predefined rank. For example, 523.25 Hz return C5, and 784 Hz return G5. If no match is found, it returns minus. Get not common node. This function finds the most frequency node in array by counting each node. If not are found, it return minus. Example, C5, D5, C5, D5, C5, return C5. Let's see code in Arduino Mega. Since our code is quite long and complex, we decided to divide it into 7 parts to make it easier to understand and explain. The first one is testing. In this part of the code, we include 3 libraries for controlling the OLED display. OI.h and download I2C communication. Adafruit CFX provide basic graphic functions, and Adafruit SSD is for working with SSD OLED screen. We'll set their skin size and create a display object using those parameters. The -1 means we are not using a reset pin. This setup is what let us show tick and graphic on the OLED throughout the pitch Hangman game. In the sections, we define the pin number for all components connect to the Arduino. PT and new word is for starting a new word, connect to pin 3. PT and submit the answer on pin 22. LED pin is the main game state at LED on pin 42. Buzzer pin connect to the buzzer on pin 4. State at LED is used while adjusting the score. Hot pin is analog A1 used with a potentiometer to change the score. In this session, we define the pin number for component connect to the Arduino. PT and new word start a new word is on pin 3. PT and submit the answer on pin 22. LED pin is the main state at LED on pin 42. Buzzer pin control the buzzer connect to pin 4. State that LED is used when adjusting the score. Hot pin is analog A1 connect to the potentiometer for changing the score. This setup makes it easy to make hardware connection in the code. In the second part, game control. In this section, define variable that manage the game state. Play node store the node play in a round. Guess node hold the player guesses. Set is check if node has been guesses. Word length store how many nodes are in current word. And later place track how many red guess correctly. Displaying show if the game is active, and score tag the player total points. The variable are key to handling gameplay, guesses, and scoring. In this part, we define variable for handling input and output. Input store incoming message or command. Mode track the current program state, like game or summary mode. Summary node hold the node that player need to guess. Last live frequency store the mode recent detect frequency. This variable allows the program to respond correctly during gameplay. In the final sections, we define variable that handle timing and delay throughout the program. Last part variable store the previous potentiometer value to detect changes. Last score change time track when the score was last update. Last blink time help control the LED blink interval. Last submit time ensure cooldown between submit button presses. Last part check control how often we check the potentiometer. We also define constant for our timing. Square default is set to 200 ms to avoid false score changes. Blink interval is 80 ms for LED blinking. Submit cooldown is 1000 ms to prevent repeat submission. In the third setup. In the setup section, we configure everything necessary for the program to start running properly. Here a breakdown of the key setup. 1. In setup, we use the pin mode function to set up the pin for different components of the Arduino board. 2. Reading potentiometer value. We use analog read hot pin to read the value from the potentiometer and store it in last pot value. This will be used later to control the score. 3. Serial communication. Initialization. Serial begin and serial 1. Begin are used to start communication with external device like a computer or another microcontroller. 4. Random number initialization. The random seed analog read A0 function initialize the random number literary. They're using a value from the analog pin, ensuring that random value differ each time the program runs. 5. Display setup. We initialize the OLED display with display.begin. After that, we clear the display and show initial data like the score, display digit score, and a welcome message, so welcome screen. 6. Waiting for button press. The last part of the setup wait until the user presses the New World button, signaling that the game is ready to begin. 4th, main loop. In this loop function, the program continuously runs to handle the gameplay and process input-output in real time. Here, how it works. Serial data processing. If there is incoming data from the serial, the program calls the serial input to process that data. New word button. When the BTM new word button is pressed, and the first time it's been pressed and the game isn't playing, it generates new underscore with generate new underscore and play random node with play random node. When the button is relayed, it resets the new word presses state to false. Score reset. If both the BTN score CTRL and BTN submit button are pressed at the same time, the program reset the score to 0 and update the display with display the score. Then print score reset to 0 to 0 monitor. Submit button processing. When the PTN submit button is pressed and the time since the last press is longer than the cooldown period, the program calls show correctness to show the correctness of the guesses and update the last submit time. Potentiometer score control. Every 50 milliseconds, the program checks for a change in the potentiometer value by calling handle score control. Now, which is used to adjust the score bit on the potentiometer reading.
Next, display function. Show welcome screen. In this function, we are display a welcome screen on the OLED display. First, we set the text size to be larger so the message is easy to read. Then, we set the text color to white. Next, we set the position of each line on the screen, starting with welcome at the top, then pitch in the middle, and finally Hangman at the bottom. Lastly, we call display function to update the screen and make sure the text is shown as we define. Next, generating underscores. In this function, it sets up the screen to show underscores for each letter in the Hangman word. First, it clears the display so it starts fresh. Then, it randomly picks a word length between 3 and 5 letters and stores it in word length. It also resets the letter place counter to 0. The starting position for the line is set at x10 y32. Each line is 16 pixels long with 20 pixels of sped between them. I will draw one line for each letter using draw line function and also prepares array to track the node play and guess. Finally, it calls display function to show the underscores on screen. Next, show frequency. The show frequencies function will show the detected frequency on the screen. First, we clear the lower part of the display to remove the old frequency. Then we set the text height, move the cursor to the position x20, y50, which is near the bottom of the screen, and set the text color to white. Finally, we print the new frequency with 2 decimal places, followed by hertz. Next, show correctness. The show correctness function checks if each guess node matches the correct one. First, it sets the starting position for showing the symbols and create a correct count to track how many are right. Then, it uses a loop to go through each node. If there are guesses at that spot, it compares it with the original node. If it's correct, it shows star. If it's wrong, it shows exclamation mark. After that, it updates the screen, increases the score based on correct guesses, and make sure it doesn't go over 9. Finally, it shows the score on a 7-segment display. Next, display digit. The display digit function displays a single digit on a 7-segment display. It takes an integer num as input and loops through each of the 7 segments, A to G, using digital write function to turn each segment on or off based on the digit pattern defined in the digit array. Now, let's take a look at the gameplay and node functions. First, the play random nodes function plays a series of random nodes and shows them on the screen to give the player clues. First, we set its playing to true and turn on the LED to show that nodes are being played. Then, we clear the screen and call generate new underscore function to show blank spaces for the word. Inside the loop, we randomly pick a node from the nodes array and store its index in play nodes. We play the node using tone function and stop it with no tone function after a short delay. This gives players a moment to hear each note clearly. After our nodes are played, we turn off the LED and set its playing to false. We also use serial.print function to lock each node to the serial monitor for debugging. The handle score control function mimics the player score using input from a button and a potentiometer. First, we read the potentiometer value with analog read and store it in hot value. Then, we check if the score control button is pressed by reading from button score control. If it's pressed, we continue. While the button is held, the LED blinks every few milliseconds, using digital write to flip its state. It's still the player that score control is active. Next, we check if the potentiometer has moved enough, about more than 10 minutes, compared to the last reading. If it turned up and the score is below 9, we increase the score. If it turned down and the score is above 0, we decrease it. To avoid rapid changes, we only update the score after a short delay, 200 milliseconds. If the button is not pressed, we turn off the LED and update last hot value to keep track of the last potentiometer position. The place detected node function shows the detected node on screen and updates the player guesses. First, it checks if all the letters in the word have already been guessed. If so, it exits the function. Next, it trims any extra spaces from summary node and finds its index using getNodeIndex function. It then stores this index in guess node and marks the current spot as gates. The cursor position is calculated based on how many letters have already been placed. The nodes is then printed on screen. After that, it calls showFrequency function to show the frequency value just below the node. Finally, it increases the letter plate counter to prepare for the next node. Next, the getNodeIndex function searches for a given node name in the nodes array. It looks through all 12 nodes and uses string compare function to compare the input node name with each node in the array. If a match is found, it returns the index of that node. If no match is found, it returns -1 to indicate that node wasn't recognized. Now, let's move on to the input functions. The parse serial input function is used to read and interpret input data from 01, which is typically connected to an external device. The input is expected in a comma-separate format like live, xxx, number of frequency, or summary, C5. The command serial1.read string until it reads the incoming serial message until it hits a new line character and store it in the input string. Then the program finds the positions of the first and second commas to help separate the data into different parts. If a comma is found, the function extracts the mode, either live or summary, into the variable mode. If the mode is live and there is a second comma, it extracts the frequency value and converts it into a float, storing it in last live frequency. If the mode is summary, it reads the detected musical note, for example C5, into summary node and calls the placeDetectedNote function to display it on the OLED screen. Lastly, it prints the received frequency and node name to the serial monitor using serial.print for debugging and monitoring purposes. Now that we explain the code and components, let's see in the action. Here, our demonstration with the actual device. We prepare 2 scenarios, one where all the answers are correct, and another where some guesses are wrong.
This is created with the help and inspiration from YouTube, ChatGPT, the Arduino website, and Conan the movie. Here, this is a comparison between original code and my modified version. This is our member in project. And last, thank you for listening to our project.
Bye bye.
Bye.